Welcome to the video key for exam 2. So we see here that in the first question we have a reaction. We're asked what the rate equation is for the forward reaction, and we can't answer this question because we don't have a mechanism, we don't have any experimental data, we have nothing. So that tells us that really there's the only possible answer is it is unknown. In the next question, we have a reaction and we do have some data. So in this case, we want to find the order of the reaction in B. So we look for a place where A is unchanging and B did change. So these are the initial concentrations, and we see that B was cut in half, but the rate was not cut in half, it was cut by a factor of 4. So the factor of 4 is equal to 2 squared, so we can see that this is second order in B. Two gas phase reactions below, what reaction would have the largest steric factor? So looking at this, remember the steric factor P is large if it's easy to orient correctly. So if you can orient to the reaction coordinates, in other words, if the molecules can line up correctly, and that's not hard, then P is large. And P is small if it's really hard to get to. So for instance, if we had two spherical molecules with no structure, we can see that if they hit, they're oriented correctly by definition. But if we imagine something with some sort of complex molecule where perhaps this has to hit at exactly these two sites or something like that, that the odds of colliding correctly go way down, so P would be small. So make sure you don't confuse steric hindrance, which you learned about in organic chemistry, which is this bulk getting in the way of molecules approaching each other, with the steric factor P, which is about the orientational complexity of the molecules. So the less complex the molecules, the higher the steric factor. So that would be these, right? So we're going to have the second reaction is going to have a larger steric factor, because we could imagine even if this first molecule spins around 180 degrees, it's still lined up correctly. And if this one spins around 180 degrees, it's lined up correctly. Whereas the second reaction, if we spin around the AB molecule, now the B part of the molecule is not lined up correctly to collide with C. And the same thing's true over here. So the steric factor for the second reaction should be approximately 4 times bigger than the first, all else being equal. Which plot corresponds to a reaction that is first order or pseudo first order in A? So we can see we've got a log plot over here, and we know that the integrated rate equation for a first order reaction, if the reaction is looks like the reactant's A, we could say that the log of the concentration of A is equal to negative kT plus the log of the original concentration, the initial concentration of A. So certainly we'd expect to get a linear plot for a first order reaction, or a reaction that we're running in a great excess of the other reactant, and so its concentration is not changing, so now we're pseudo first order in A. All right, how does a decrease in the steric factor affect the entropy of activation? So what you want to do is make sure that you have the idea that the steric factor helps determine how big the pre-exponential factor A is, and that in turn is related to the change in entropy upon forming a transition state. Those things are all in the same sort of mental bucket, right? So if we made the steric factor worse by making it smaller, that's also going to make your pre-exponential Arrhenius factor smaller. And what makes the pre-exponential Arrhenius factor smaller? It's making your entropy of activation worse, either more negative, or going from positive to negative, or going from a positive number to a less positive number. So it's just decreasing in value. So all of these things are linked. Okay. Certainly for gas phase reactions, we expect the delta S of activation to be a negative number. So we're going from, especially for bimolecular reactions. All right, so we expect the entropy of activation to be less positive or more negative. decreasing in value. Okay, so if you think about, if you go from this type of reaction, which would have a relatively high steric factor, to this type of reaction where the molecules have defined ends and they have to be oriented a certain way, maybe they have to be end-on approach and they have certain ends, then this would have a much smaller, this is large p, as we discussed earlier, this is small p. You can see that because we have to line things up to start to approach the transition state in that second case, we're decreasing in entropy. We don't have rotational entropy when we're forced to adopt certain orientations. And so having a small value of p is the same as having a small delta s, or more negative delta s. Okay, decrease in steric factor and affect the enthalpy. So there is just no effect. There's no effect. So the enthalpy of activation is just related to the activation energy, because that's just a function of we have to start breaking bonds to get up to the transition state from our reactants, and so it's not a function of how hard it is to get a line. That's a function of bond strength. So it's unchanged. All right, so now we have a reaction, and imagine that we're tuning the activation enthalpy. So we're taking our activation entropy, and making it more negative. Okay, so what's that going to affect? We can see that's going to make it harder to put together our transition state, not in terms of energy, but in terms of reducing the microstates of the components as they assemble to become the transition state. So that's going to change our pre-exponential factor A. Oh, and of course, since the rate constant is a function of the pre-exponential factor and this exponential energy term, if we decrease the pre-exponential term, that is also going to decrease our rate constant. In the next question, we're going to this time just change the activation enthalpy. And here we're making it worse by making that bigger, right? So we know that there's a linear relationship between that and the activation energy. And the specifics of that depend on the molecularity and the phase, whether it's solid or gas. But there's always a linear relationship between activation enthalpy and activation energy. So if we make activation enthalpy worse, that's equivalent to making the activation energy worse, bigger. And that's going to make our rate constant small, all else being equal. And here, similar problem, where we're taking our entropy of activation and it's really acting the same question, just another way. What's the relationship between activation entropy? We know it's with the pre-exponential factor A. So if we're going to, in this case, make this better, right? We're making it easier to make the transition state because we're making the entropy of activation more positive or less negative. We're adding to its value. That's going to make the A constant bigger. So A is going to increase. All right, consider the mechanism below. What's the rate equation for the reverse reaction? So this is similar to the one at the start of the test, but it's different because here we specify that this is a mechanism. So right away we know this isn't just telling us that the stoichiometry is 1 to 2. We're talking about the forward process being unimolecular and the reverse process being bimolecular. And so we know we can predict the order of the forward and reverse step. And so here we're looking at the reverse step. So we know it's going to be K prime times B squared because it's bimolecular, so it has to be second order in B. Consider two reactions. They have equal values for rate constants at room temperature. Which one will have a larger value for K? So this one, you have to watch your intuition because it's going to lead you astray. So let's just use the linear version of the Arrhenius equation. So we take the Arrhenius equation and we take the log of both sides, and we get the log of K is equal to negative EA over R 1 over T plus the log of A, where A is the Arrhenius pre-exponential factor. And we can see if we call this X and we call this Y, that our slope is the negative of the activation energy over R. So since activation energy is usually positive, this is going to give us a negative slope. And what this tells us is that over here on the left, where we have high temperatures, since this is a reciprocal actus, we're going to have high values for K. All right, so we have two different reactions, okay? And at room temperature, they have the same rate constant, K. So notice that as we go to higher temperatures, that one of them is going to have a higher value of K. So this is the faster at high temperature. And notice that's also the one with the more negative slope. If it's the more negative slope, we can see, since the slope is the negative of the activation energy over R, it's the bigger activation energy. So higher activation energy is the one that's going to speed up more. And we can think about this conceptually in that, what is activation energy? Well, let's write this out. K is equal to A to the negative EA over RT. So if we look at this, what happens to a K as we make activation energy really big? It gets small, right? But it gets small in proportion to the temperature. So if we go to really high temperatures, we can overcome the large activation energy and still have a large K. So basically, EA, the activation energy, tells you how temperature sensitive the reaction is. So a reaction with a high activation energy will slow down more at low temperatures, and it will speed up more at high temperatures. Okay, so so the more your activation energy is, the higher the activation energy is, the greater your temperature sensitivity. So looking at these reactions, we can see that if they were the same at room temperature, despite one of them having a higher activation energy, it must be that this reaction here also had a larger value of A. Now we're comparing two gas phase reactions, and all the bond lengths and energies are the same, and we're supposed to make some prediction. So if we look at these, we can see B is going to react with C to form a bond. We're breaking the CD bond. And here A is reacting with B. We're making an AB bond and breaking a BB bond. Now, since all the bonds are the same strength, this means that delta H for the reaction will be 0. Okay? But it also means that we expect that the activation energies will be similar, right, for all of these, because we're partially breaking bonds as we form a transition state. We're breaking bonds of the same strength. So activation energies for these two, so we can say EA1 should be about the same as EA2, but not the Arrhenius pre-exponential factor, because if we look at this, there's more ways to get this reaction to be oriented correctly than there is the first one, right? If we flip around the first molecule or the second molecule in this second reaction, they're still going to be able to form an AB bond. We can't do that with the first one. So we expect that this second reaction is going to have a greater value for the Arrhenius pre-exponential factor A. And as we saw earlier, the greater the Arrhenius pre-exponential factor A, the greater the entropy of activation. Okay, we could say it's the less negative, or for some reactions, especially solution phase reactions, it could even be positive. So that means we are looking over here at the entropy of activation. It's going to be either more positive or less negative, or it could even switch from being negative to positive. Okay, this is the reverse case. So here, if we look at these are both symmetric sticks, right? We have BB and DD and AA and BB. So we expect that A1 be approximately equal to A2 for the two reactions. But what about the activation energies? So we can see we're starting to make a BD bond, but we're breaking a DD bond in the first reaction. In the second reaction, we're making an AB bond, but we're breaking a BB bond. And they tell us BB bonds are much stronger than the others. They have a larger bond energy. So since we have a half, we're going to, as we approach the transition state, we're going to have a half broken bond that is a BB bond, right? So if we drew the transition state for this, we'd have the start of a bond between A and B, and then we're also breaking a bond with that other B atom. And since this is a super strong bond, that's going to cost us some energy. So we expect this second reaction to have a much higher activation energy than the first one. And what does that mean? Well, we can also say that the activation enthalpy for the second reaction should be greater than the activation enthalpy for the first reaction. So a more positive activation enthalpy. Okay, so we're supposed to find from this RC diagram, this reaction coordinate diagram, what the activation energy is for the reverse step. So reverse step, we're going from point A to point B here. So just draw a little thing here. We're doing this. This is going to be EA for the reverse step. And if we look at this, we can see that each of these tick marks is about 50 kilojoules. So it's about 200 kilojoules per mole. All right, two-phase elementary reaction mechanism steps. Okay, so we've got two gas phase elementary reactions, and their steps in a mechanism. And so we're comparing something like this versus something like this. Okay, so these are not reactions, these are mechanistic steps. So comparing these steps, we're trying to say which one would have a more negative entropy of activation. And we know it has to be this one, because here we're going from 2 moles of gas, and this just shows the transition state here. So in the first one, you're going from 1 mole of gas to 1 mole of gas. In the second one, you're going from 2 moles of gas to 1 mole of gas. And we know that decreasing moles of gas is going to decrease our entropy. So this is going to be a very negative entropy of activation, even if we don't have to orient these. Like even if these are perfect spheres, we're going to lose entropy just because we went from 2 moles of gas to 1. So more negative entropy of activation for a bimolecular step. So for diffusion-controlled reaction, we know the rate constant for this reaction, and this is going to be true for bimolecular diffusion-controlled reactions, that it's just a function of the temperature and the viscosity of the solvent. So in this case, it's just we have to make sure we use the right units here. You can see if we plug in 8.314 joules per mole per Kelvin, we're going to have everything in SI units. So we'll check those at the end to see how that turns out. So we have 320 kelvins. We've got a viscosity for our solvent is 0.0056 Pascal seconds. Okay, so looking at this, we put everything into SI units, so our rate constant is going to come out in SI units as well. So when we plug all this in, we end up with 1.26 or 1.27 times 10 to the 6th, but we better see how the units cancel. So the kelvins cancel kelvins. We have a left-hand unit of mole, which we're going to need anyway. But what happens, and a per second, but what about a joule divided by a Pascal? So if we take our joule, what is that equal to? If you can, one way to remember what a joule is to remember that kinetic energy is equal to 1/2 mv squared. So you can see a joule is going to be a mass unit times a speed unit squared, right? So I've got mv squared. And a Pascal is equal to a Newton per meter squared. And you may remember that a joule is a Newton meter, right? So if we think of a Newton, so we can go ahead and let's cancel that. So if we take our joule, we've got kilogram meter squared, and let's just go ahead and put the meter squared up here and the second squared on the bottom. So we're taking care of our joule. If you've got a joule, and on the bottom we have pascals. So let's put a Pascal down there so we know it's a Newton per meter squared. That's supposed to be at 2. And let's just say what a Newton is. So a Newton, you can always remember what a Newton is if you use F equal ma as your mnemonic, because then a Newton is going to be a kilogram meter per second squared, right? So it's force equal mass times acceleration. So kilogram meter per second squared. So let's get rid of our Newton and replace it with a kilogram meter per second squared. And then we can see our second squared is going to cancel, and this meter will cancel one of those, and our kilograms will cancel, and we end up with what was a joule divided by a Newton is going to be a meter cubed. Okay, so the joule divided by a Newton is, or a joule divided by a Pascal rather, is equal to a meter cubed. Okay. Another way of thinking about this is a joule is equal to a meter cubed times a Pascal. Think about work. Work is equal to the negative integral of pressure dV. So we know if we take a pressure unit and multiply it by a volume unit, if they're both SI, we must get the SI unit for joules. So that's another way to remember. Anyway, if we divide a joule by a Pascal, we get a meter cubed. So that means we can cross this out, and we end up with a meter cubed. So notice our units are meter cubed per mole per second. And that's not what we're used to using for chemistry units. So for chemistry units, we probably ought to switch this to liters. So we've got 1,000 liters is 1 meter cubed. And then we can get sort of units that we're used to for a rate constant. So we're going to multiply by 1,000. So we get 1.27 10 to the 9th liters per mole per second. And if we look at this, this is the range that we talked about before for diffusion limited reactions. All right, number 27. So looking at this, we've got two reactions, and if we look at this, we can see that we've got, in one case, we've got something where we have a step where the second step has a small rate constant. So this is small, and the first one is a large rate constant. So if we were to graph our concentration of I, our intermediate, as a function of time, we can see that in this first mechanism, because we have a large rate constant building up the intermediate, it's going to build up and then it's going to get consumed. Whereas in the second mechanism, we have the K2 is large and the K1 is small. So we can see here that as soon as we make a molecule of I, it's going to be consumed in the second step. So if we look at this, I is going to essentially stay very close to 0 as we go through time. And that makes the fact that we have that, this is the steady state approximation. The steady state approximation is that the change in this intermediate as a function of time is approximately 0. That this during most of the course of the reaction, this is a horizontal line, right? Because not only is the concentration close to 0, it's approximately constant. So that is a simplifying assumption that we can't make in the first mechanism. And if we make that simplifying assumption, so this is going to be the one that's easier to. So the question was, which mechanism is easier to analyze? It turns out the first one's a real bear, but the second one we can do pretty easily, because we can say, okay, if this is true, if this key equation is true, then we can say the rate at which we make I. What's the rate at which we make I? That's the rate of that first step, right? So k. I'll call it k1 times a squared. That's the rate of the first step. That's going to be making I is going to be equal to the rate of the second step, which is going to be k2 times I times c. So we can only do this because of the steady state condition. We can't do that all the time. We can only do this if we have this slow constant followed by a fast constant. But in this case we can. And this is going to be important because if we look at the rate overall, like if we want to actually make product here, if we want to make C, we know that that's the rate of the second step. That's going to be K2 times I times B. But you can't put intermediates in your rate equation. You're only supposed to put reactants. So we have to have a way of getting rid of I. But we can do that by solving this equation, right? So we solve this equation and we say I is going to be, okay, we've got K1. We'll divide both sides by K2, and this was actually wrong. Let's go ahead and fix this. The rate at which this thing is being eaten is a function of K2 times the reactants in that step, which are I and B. So this is the rate of the second step. Anyway, if we take both sides and divide by K2 and divide by B, we'll do that. So we'll divide by K2, we'll divide by B. That's going to be equal to the concentration of our intermediate. If we plug that in over here in our overrate equation, we get V overall is equal to K2, and then we've got our expression that we made for I, which is K1 over K2, A squared over B, and then we bring down this other B that we had here, and we can see the B's cancel, and we're left, and the K2's cancel, and we're left that V overall is just K1 A squared. In other words, the second step is irrelevant because the first step is rate limiting. But we can only do that if the rate limiting step comes first. We couldn't do that in the first mechanism because the intermediate builds up and it has this giant change in concentration over the course of the reaction. So the steady state assumption works when the slow constant is first, when the rate limiting step is first, not when it's second. Determine the rate equation for the one we chose. Oh, actually, I just did that. Okay, well, we're done with that. All right, consider the reaction below. Let's make a guess about the steric factor. We're supposed to make a guess about the steric factor. So if we had two balls coming together, as I mentioned during the other part of this to make our transition state, we can see how there's no orientation effect. So we could say P is going to be approximately 1. So if we're going to make an order of magnitude guess here, let's see what this looks like. We've got a stick, which will be our nitrogen. We've got a ball, which is an oxygen atom, and they're coming together, and there's going to be some orientation that's necessary. If it maybe comes from the side, that probably won't work, but if it comes from the end, it will work. So if we imagine this, it could come from, either end, because we know that nitrogen's symmetric. So all of these would probably work, but these might not work, right? So you might imagine that depending upon how strict, like if you can get a little bit off axis, it might still work, but if you go too far off, it's not going to work. So this is just a guess on my part. I'm going to say P is approximately 0.1, but we're just making order of magnitude guess. All right, so now let's go ahead and solve this. I had a typo here when I actually did the quiz, so I was lenient and made the question half extra credit, which is why there's an adjustment on the grades. Okay, we're supposed to find the value of P, the thing we just guessed at. So we can say that K from collision theory is going to be a function bunch of different variables. Let's just go ahead and write out the expression. So we've got our steric factor P, Avogadro's number, we've got collision cross sections. Okay, and it's two different species, so we'll put IJ. We have the average of the relative speeds, and then we have our activation energy term. And if we write the Arrhenius equation below that, that's supposed to be negative there, we can see that, oh, but they both have an activation energy term, which means that the thing in the box has to be our expression for the Arrhenius constant A. All right, and we have that, so we can just solve for our steric factor P. And to do that, we're going to want to put things into the same units. So let's use SI units, and so let's convert our A into SI units and take it out of chemist units. So we said it was 10 to the 11th liters per mole per second, and we want to put this into chemist units, so we're going to, out of chemist units into SI units. So let's get rid of liters, put meters cubed, and there's 1,000 liters in a meters cubed, and now we've gotten rid of liters. So we can see that this is going to end up being 10 to the 8th meters cubed per mole per second. Okay, so we have our A factor. And now we can, let's go ahead and equate our two expressions, our expression for A to A. So we said A is equal to steric factor, Avogadro's number, collision cross section, and the relative speed. And so we can solve that for our steric factor P. So it's whatever our Arrhenius factor is divided by Avogadro's number, collision cross section, and the relative speed. And then at this point, what we can do is we have numbers for everything except for relative speed. So we have to do relative speed. And to do relative speed, we have to do the reduced mass. And we could do this in terms of molecular mass or molar mass. Molar mass is easier, so let's do this. So the reduced molar mass is going to be, let's see, we've got, I've forgotten what our molecules are. So our molecules are nitrogen and oxygen atom. So we're going to have, I'll just put it in grams first and then we'll convert it. So we've got nitrogen, so we've got 28 grams per mole. And we've got our oxygen atom, so it's only 16 grams per mole. And then on the bottom we've got 28 grams per mole added to 16 grams per mole. And that comes out to something like 10. Let's say okay, so that's 10.18 grams per mole, but we want to put this in SI units. So we'll say that is 0.1018 kilograms per mole. And then we can plug that into the expression for the average relative speed. So you've got 8 over pi, we've got RT, and then we plug in our molar relative mass. And notice that R is per mole and this is per mole, so we're good to go here. So we'll go ahead and put in 8.314 joules per mole per Kelvin. We've got 300 and near room temperature, so we're just going to do room temperature. So we've got 298 kelvins, and we've got our mass per mole in kilograms. So we can see our per mole is going to cancel out, our kelvins cancel our kelvins, and we've got joules divided by kilograms, which gives us meters squared per second squared, so take the square root. So we get 787 meters per second. So now we're ready to plug everything in. So we got all our pieces. We're going to bring this expression down here, say P is equal to, and we've got 10 to the 8th meters cubed per mole per second. We've got Avogadro's number, 6.02 times 10 to the 23rd, 1 over moles. So you can see those moles are going to cancel. We've got our collision cross-section, which was around 0.4 or so. 0.4 square nanometers. So of course we want to put that into SI units. So it's 0.9 squared. So it's, or not 0.9, it's 10 negative 9 squared. So it's 10 negative 18 meters squared. And the last bit of our equation that we're using up here is we need our speed. So we've got 787 meters per second. And then let's check our units here. We've got meters cubed here on the bottom, meters cubed on the top, and we've got per seconds here and per seconds on the bottom. So the units all cancel out because P is just a fraction, right? It's got to be a number not with units. It's got to be unitless. So we plug all this in, and we end up with 0.53. So our initial guess wasn't bad. I said 0.1, that's pretty much a guess. So it looks like there's some flexibility in terms of where that oxygen can hit on that nitrogen, right? It doesn't have to be exactly an end-on impact. There's like a cone around either end of the molecule that would work, it looks like. So about half the collisions, the orientation is going to be right for this thing to react in the reaction given. Okay, so in this problem, we've got a mechanism, and we can see we could call it a parallel mechanism or competing reactions. So one starting material drains off into two different possible products. And so this was something we did a few weeks ago in one of our activities, and we saw that we could write an integrated rate equation for A. I'll go ahead and write it, where A is equal to A naught minus K1 plus K2 T. So we can see these are both irreversible first order reactions because it's unimolecular in A, and both of them are going to be cutting down on our concentration at A. So we can imagine calling this bit here K total, right? Because they're going to be additive, right? If one is draining off a certain number of molecules per second and the other one's also doing it, that's going to add up and decrease the amount of A. And one of the things we saw from this is that because they're both draining A using the same order of reaction, they're going to decrease in their rate at the same amount. So as A gets depleted, both reactions slow down, but they slow down the same amount. So they're always going to be the ratio of reaction 2 and reaction 1, that ratio is going to stay constant. And for that reason, the ratio of K1 to K2 is equal at any point in the reaction to the product produced by K1 and K2. So if we look at the concentration, as long as we start off with no B and C, so it's an even race, right? They're starting off B and C are 0 and they're only coming from A, then this ratio of K1 to K2 is equal to the ratio of B to C. And that is the key to this problem, because we said the concentration of product B is 3 times bigger than the concentration of product C. So another way of saying it is there's 3 times more B, so the reaction that produces B is 3 times faster. So we can say K1 over K2 is equal to 3. Or we could say K1 is equal to K2 times 3, right? So because K1 is it's the faster rate constant, that reaction is going to be faster. Well, that's an equation, but we need another equation. But we have one. Here's how we have one. If we look at this, we have a linear fit, and of course it's logarithmic, which we saw earlier. That means it's first order. What is this slope? we know the slope is equal to k. So we can say, well, the negative of the slope is equal to k. So we can say 0.00146 reciprocal seconds. That's the units we're going to get for this slope. That's a k, but which k is it? Well, that's the total k. That's the overall amount that A is being drained, because this is the log of the concentration of A over time, right? So that must be the sum of those two rate constants. So we can say K1 plus K2 is equal to K total. So now we have another equation. We have two equations, right? We have K1 plus K2 equals K total, and we have this relationship that K1 is 3 times bigger than K2. So we could plug that in. So we'll plug this relationship in over here. So we'll call K1 3 times K2. And then we've got our original K2. So K1 plus K2 is the same as 3 times K2 plus K2 is equal to K total. And so 4K2 is equal to K total. So since we know what the K total is from the fit to our plot, right, because we know that the slope of this linear plot has to be equal to negative k, we now can just divide that slope, which is k total, by 4, get our k2, and then we can use this relationship over here to get our k1. So if we just divide our k total by 4, we get k2, and then we multiply that by 3 to get our k1, the faster reaction, we get 1.095 10 negative 3 reciprocal seconds. All right, I think this is our last problem. So we have a unimolecular solution phase reaction, and we're supposed to use the entropy and the enthalpy of activation. So there's a negative sign here, which some of you missed because it was on the edge. So I basically, if you used a positive number here, I just said okay. I didn't mark off for that. So because all your work was right. So doing this, we have to figure out how to calculate these. And some of these equations are on your equation sheet. We'll just work from the ones that are on your equation sheet. Okay, so we've got a unimolecular solution phase reaction, and for those we have that our enthalpy of activation is going to be this is backwards. That's right, is activation energy minus RT. And so then if we solve for activation energy, we can see that we have to add RT to our, to our delta H of activation. So the activation energy is going to be 92 kilojoules per mole, plus we've got 8.314 joules per mole per Kelvin. We've got our 325 kelvins, and then we better put this into kilojoules. So we've got 1 kilojoule is 1,000 joules. So now I can cancel all this, and I end up with kilojoules per mole. Okay, so we get 94.7 kilojoules per mole. Okay, and now for the Arrhenius parameter, the correct expression, and this is, I'll just write it out as it is on your equation sheet. For this phase of reaction with this order, you end up with KT over H. You've got one factor of just an exponential 1 of 2.7 essentially. You've got E to the activation entropy over R. And then the last part is E to the minus EA over RT. And once again, we can compare this to the Arrhenius equation. And when we do, we can see, we can just chop off this bit. That's just going to be our activation term. And then we can identify which part of our rate constant comes from the pre-exponential factor. So our pre-exponential factor is going to be kT over Planck's constant. We've got 2.71. We've got E to the activation entropy over R. So now we can plug in those numbers. Let's go ahead and plug those in. So 6.626, 10 negative 34 joule seconds. On the bottom we have, oh, I've got it backwards, don't I? I'll just go backwards. Okay, let's try that again. So we got 1.38, 10 negative 23 joules per Kelvin. And if you do make a mistake like that, you'll catch it when you do your units. We were at some specific temperature. We were at 325 kelvins. And the bottom we've got Planck's constant 6.626, 10 to the negative 34 joule seconds. E to the 1, and then E to the entropy of activation, which we said was negative 185 joules per mole per Kelvin, and we're dividing by R, 8.314 joules per mole per Kelvin. So we can see these units cancel out, so we can feed this straight into this exponential function. Kelvins cancel kelvins, joules cancel joules, and we end up with 3991 as our Arrhenius factor. Oh, and we forgot our units, it's reciprocal seconds. And notice we did see that these units make sense for the reaction because the reaction was unimolecular solution phase, so we know it has to be first order, and if it's first order, it has to have units of reciprocal second. The answer is an A factor, reciprocal, an A. So the Arrhenius pre-exponential factor is here. And we can see that because our activation entropy was so negative, we ended up with a pretty small Arrhenius pre-exponential factor. That's the end of the key for exam 2. Thank you for watching.